Hello, my name is George Velasic. For our undergraduate project in this data communications class, the first part I will be doing asynchronous transfer mode. It'll be a general protocol overview. At first I was really dead set on doing IPv6. I figured it might be a good idea to kind of burst out of my bubble a little bit and look at maybe some protocols that aren't as prevalent today and ones that I didn't know about. I learned a lot. I went from thinking that ATM meant automated teller machine to actually kind of understanding exactly what it is that the ATM model does represent. So moving along, the presentation outline is going to follow the basics on what exactly ATM is. I'll be touching up on a basic definition and to give people an idea of what it is. Then we'll be bursting into the ATM protocol reference model. And people will see a lot of similarities, I'm sure, to the OSI model or to other models as well. Probably see a lot of similarity in terms of like packets, etc., and how things are transmitted. Maybe by looking at it from a circuit switch perspective. I'll be looking at the anatomy of everything together, the upper layers, the AAL, the ATM layer, the anatomy of that as well, and then the physical realm. We'll be looking at the VCCs and the VCPs, kind of trying to give everybody a good visual representation of how that does work, how the data is transmitted along the medium via these virtual circuits. Why IP has kind of prevailed over ATM is considered more of the standard to go with. And then lastly, we'll have the references for you to take a gander at. So again, what is ATM? So ATM, as a base definition, ATM is an acronym for asynchronous transfer mode. Again, not to be confused with ATMs that you draw money from. I was naive enough to think that at first. Decided out of curiosity again to look to see what ATM was really about. Learned a little bit about it. At first it was hard for me to find a lot of information. Found a couple journal articles that really helped me understand everything better. A couple Cisco resources. But basically what it is, it's a high-speed network standard designed to support voice, video, and data communications and to improve utilization on high-traffic networks. It uses same-size packets. They're uniquely known as cells specifically for ATM. And what it's good for is it helps minimize the jitter and optimize the transmission over the multiplex streams. As I'll talk about it a little bit later, the jitter is not that big of an issue nowadays, but then it really was, and it really helped on error control. Now, this is a low latency and high reliability stream for this protocol, and it is connection-oriented packet switching technology. So it's not just like the datagram concept of you can go along any route that you can to the destination and then get put back in order, back in place. Everything will follow that same exact stream from host to destination. But there are a little bit of intricate details that I'll cover a little later there. Now, this is much more prevalent in the past as IP protocols have taken precedence in most situations. This is the whole suite itself. So IP has really grown over time, and while ATM was expected to kind of be this great backbone and to be a worldwide international system, it's kind of died off as of recent. There just are a lot more practical fits than ATM, but it still does have its purpose in some networks. And ultimately, the primary goal of ATM was to support a diversity of traffic with various service requirements. So not just to be like a one-trick pony, like just specifically passing over like voice communications, data communications, images, etc., but to cover the whole gamut and pass everything along. So the ATM protocol reference model, it was introduced by the ATM Forum. One of my first cited sources was two gentlemen from college, I don't remember, I think it was University of San Diego. They really did a lot of research on this in the early 90s. And like they said, it was a small group, a handful of people, and then by the late 90s when they publicized and wrote more journal entries, it had ballooned up to a couple hundred different representatives for the forum. Now, it's based on standards set forth by the International Telecommunications Union, or the ITU is the acronym. And the reason I distinctly separate the two is because the ATM forum was not like an actual a group like ITU. It was more of like independent people with ideas. It was a general forum. There was no like exact leadership or anything like that. You wouldn't consider it one of the same protocol groups like ITU. Now, upper layers adapt to ATM protocols which pass to the lower ATM layers, which we'll see on a little diagram later. And ATM-defined layers pass data to the physical layer where it's transmitted onto the physical medium. So what we're looking at, you'll see like where it's represented on the OSI model if you were to compare it side by side. But basically everything's going to be passing down from the user. The data is going to go from the user. It's going to be transmitted into the packets. It's going to move into the AAL and the ATM layers, move back down, get placed onto the physical media, and get passed along. Okay. Now, ATM itself never did quite gain a foothold in wireless transmission. It was possible, it was done, but it was never that prevalent. It was not that popular, because by the time it came around, there were a lot better options to choose. Now, the ATM protocol reference model, this is the anatomy right here. We have the higher layer protocols, which would be like application, etc., all the way down to the network, which would end about right here if we were looking at the OSI model. This is going to cover the control plane, the user plane, and then the management planes. The management planes will be set up with plane management and layer management respectively. Then you have the ATM adaptation layer, which will be the convergent sublayer, which passes down to the segmentation and reassembly sublayer, or the SAR for short, which will then hand down to the ATM layer, which then hands down to the physical layer, which is the transmission convergent sublayer and the physical medium sublayer. So as you can see, just like any other layers, it's going to hand down. It's going to have its different distinct rules and its own little like setup as it moves down. But these are independent of each other. So first we have our upper layers. The upper layers are responsible for accepting the user data. They're going to separate it into the packets because that still does happen around where the network layer would be on the OSI, and it's going to hand it down to the AAL, not to straight to the ATM layer, but to the AAL first. In order. So the control plane is what generates and manages the signal request. The user plane is responsible for the transfer of data. Now your management plane, like I said, will be broken into two different parts, like back here with layer management and plane management. And again, this is just a very generalized explanation, as going into any more detail would take up way too much of your time. But the layer management manages layer functions, i.e. the protocol failure and the detection of errors as it's passed. And then plane management manages the functions related to the entire system as a whole. So then this is going to pass down to the ATM adaptation layer. This is the first of the major layers that really deal with ATM. This is the AAL for short again. Now in conjunction with the AAL and the ATM layer, this is comparable to the data link layer of the OSI model. It's kind of like similar things are being done that you would see done on the data link layer. Just going to have a little bit different names, and it's, obviously going to have a little bit of a different process. So what we do have is we do have the convergent sublayer, which the convergent sublayer, it encases the user service data between a header and a trailer. Header and trailers, which we'll see in a lot of different instances on a lot of different layers, they pack on their own different header and trailer information that it'll give it information on like what kind of data is being passed and then error correction, etc. And then you have the segmentation and reassembly sublayer, which is exactly how it sounds. Oh, and that was what I said earlier, the acronym, it's SAR for short. What it's going to do is it segments the data stream into fixed size cells. And I say that again, it's fixed size cells. So every single cell is going to be the exact same size, regardless, like there might be a variance in speeds or data rates, but the cells will always be the same fixed size. And this is going to segment those data streams into those fixed cells for the lower layers, so that way it's readable by the ATM switches, because these are specifically ATM switches. And then it's going to also take those cells and reassemble the payloads into a format that the upper layers can understand. So then after that, when it's reassembled, it's going to be something that the upper layers can logically understand and pass forward. So then I'm going to look now at the classes of data that I said before. The classes of data will come right into this convergent sublayer right here. You see that kind of like what the data is that we're dealing with and how it's going to need to be modified to be transmitted. We have Class A, which is the Constant Bit Rate Service, or AAL1 for short. It supports connected-oriented service with the constant bit rate. We have Class B, which is Variable Bit Rate Service, or AAL2. It supports connection-ordered service where the bit rate's variable, but it requires bounded delay between the packets. So there's going to be a variable bit rate depending on a whole litany of different things on how fast the rate is. But everything, again, will still be, like I said, it's going to be the same fixed size cells. And it will require the bounded delay between the packets. Now, Class C is a connection-oriented data service represented by AAL3/4 and AAL5. That is not AAL3 and AAL4. They're actually bundled kind of into the same thing. This has a variable bit rate like Class B, but it does not require the bounded delay for the delivery. Then there is Class D, which is a connectionless data service, which is AAL3/4 and AAL5, like Class C before it. It includes data network applications that don't require a connection before data transfer, as well as datagrams. So it's going to help transfer those different ones like datagrams over. Which datagrams, again, are like if you saw like in a packet switching network, as opposed to having that one set line, it can find the best route to meet the destination and then be segmented in the right order or reassembled in the right order upon entry. What this is going to do, Class D is going to find a way to where it can systematically pass that along the ATM switch and make sure it follows the ATM logic. ALL5 is often used as a class in most instances as it covers connection-oriented and connectionless data services. It encompasses everything, so covering that entire umbrella, it's most optimal to use in most situations. Now the ATM layer, in conjunction with the AAL, it's comparable to the data link layers, the OSI model, again. It's responsible for cell relay and the cell multiplexing. So the relay is going to be the passing of the cells through the entirety of the ATM network. The multiplexing is the creation and sharing of the circuits over the physical link that are made between the source and destination. Now I say again, these are virtual circuits. You're not going to have any sort of physical median right there, like suddenly like wires are growing out of nowhere. We need to understand that these are virtual circuits, but they pretty much follow the same logic that like a regular circuit would. And multiplexing is going to be like the multi-circuits on the same link that are following to go to their destination. So again, cell relay and cell multiplexing are the main responsibilities, as well as switching and flow control are the two main directives of the layer. Now the two interfaces in the ATM network, there are small differences in the cell header. I'll explain it on the next diagram that I show. But there's the user network interface and the network interface. Now user network interface is going to have a connection between the endpoint of ATM and the ATM switch. The network interface is going to be specifically between two ATM network switches over the network. Okay? So right, like I said here, so the anatomy of an ATM cell. So what we're looking at right here, this is the UNI format, which would be the most common in most instances, the user network interface. And you are going to have here, you see the legend right here, we have the GFC, which is going to be 4 bits, the generic flow control. We have the VPI, which is going to be 8 bits, which is also known as the virtual path identifier. And then we also have the virtual channel identifier, which is going to be 16 bits right here. Then after that, we have the payload type, cell loss priority, header error control right here, 12 bits, 3, 1, and 8 respectively. And then we have the payload, which is going to be 48, not bits, but bytes. So our header is going to be 5 bytes total, or 5 octets total, making up 40 bits. And then our payload, 48 bytes, or octets, and 384 bits. So it's always going to be 424 bits long. This is where that fixed size comes into play. The differences you would see on the NNI would be that there would not need to be any generic flow control there at all, because it's just going from switch to switch on the ATM network. But then what you would see then is you would just see a bigger VPI or virtual path identifier. So instead of having like 8, you would have the 12 bits. So some more about ATM cells. To explain this, the GFC, the generic flow control, it only appears at the user network interface. Like I said, it controls the flow of the traffic for a myriad of QoS quality of service reasons, and it helps with short-term overload in the network. The VPI is the routing field for the network. The VCI is the routing field for user to user. Okay, so make that distinction there. Routing field for VPI, network. VCI, user to user. So the payload type is the type of information in the payload. It's going to be 3 bits long. So this is one thing to remember, either zeros or ones. There's going to be, I'm not going to put the little the table on what every one means, but I'll give you a gist of what each bit would represent. The first bit being a 0 would mean the user data cell. The 1 means that it's a management or has maintenance information that is passing along. The second bit denotes congestion. So if there is or there isn't what you need to do. Third bit is going to be used to distinguish between the 2 different ATM service data units, or SDUs. Cell loss priority is, again, in the event of congestion, it denotes priority and what should be done. So it'll pretty much tell you, like, if you pass that threshold, there might be a chance that this is going to be dropped, or it'll let you know, like, hey, if what needs to take priority or precedence over something else in terms of getting passed as data. So, for instance, voice generally takes more priority over data, etc. HEC is used to detect and correct errors in the header. Again, like the name, header error correction. And then the payload is going to be the information or the data in the cell that is to be sent, the body of everything that we really want to get to where it needs to go, or what we want to see. Now the physical layer is like it is anywhere else. It's a physical medium. It's comparable to the physical layer of the OSI model. It manages the placement of the signal onto the media and its transmission as well. There are 2 sublayers here, the PMD, or the physical medium dependent sublayer. It specifies the physical media being used, including the connectors and the ports and everything that are being used. It synchronizes the transmission, sends continuous flow of data bits with timing information, and it supports 2 types, optical and electrical. So key right there, it does support optical. Then there's transmission convergence, or TC, which controls cell delineation, header error control, sequence generation and verification, cell rate decoupling, and transmission frame adaptation. Running a little short on time here, so I'll try to speed it up. This is the VCCs and VCPs section. This is a nice little picture to get you an idea. This is the transmission path. So this transmission path is just what it sounds like. It is the physical layer, physical medium. So this is the medium. Imagine the wire right here. And then you have your virtual, not actual physical paths, and then the little virtual channels inside these paths. Okay. So the virtual channel connection, it's the basic unit of switching in the ATM network. You could think of it as a virtual circuit, like I said earlier, much like what is used in the telecommunication system that we grew up with. More like the virtual circuits or the circuits that you would have seen before. So it's identified by a combination of VPI and VCI in the cell header. So all this right here is going to help give us an idea, or that little bit of information. The VCC is like the single lane of multiple lanes that make up the roadway. That's the way I like to see it. When I try to visualize how everything works, we have all the data flowing. So while we do have this one lane road, like we have all these different lanes possibly going in the same direction. Everything is all bundled up together. And this is used for control signaling, network management, and routing onto the network. We have the virtual path connection, which is identified just by the VPI in the cell header, just by the VPI. So just going from path to path. But we have a bundle of virtual channels, which is switched based off of the VPI. So this right here is the bundle of all the channels. These are remapped as necessary at each ATM switch, but all VCCs have the same ending point. Now this is not to say that they're not all going to follow the same path, because they will, much like on, like a virtual circuit system would in packet switching technology. but it's going to remap as necessary at each ATM switch, because what it's doing is this is dependent on the ATM hardware. These are like the headers and the trailers. This is where everything's going. Where it's passing it on is based to the ATM switches, and then after that it'll get passed on to the end user. This is of local significance only, again. Of local significance only. Once you get out of the local area and you're moving on to the next ATM switch, it will redirect accordingly to what's the best path, or the open path. So VPC is like the whole roadway of traffic, all the lanes going. And then the control costs take up much of the expense of data traffic. This is one thing that I wanted to expand on. So that was one of the big issues, was that control cost got to the point to where that control cost and that overhead was costing so much money from the data traffic because it was taking so much of the possible data rate and transmissions. VPCs helped alleviate much of these costs because it's bundling it all up and saying, okay, like instead of having to have all the control information of every little thing, everything that's kind of going the same direction will group together and ship off together for the most part. So it really helps cut down on a lot of that control information. So why IP over ATM? Because that's one thing that I kept seeing. The one thing that I was really trying to research is, okay, well, I'm hearing all this about ATM, and it was like past tense. So why is that? I looked up different things that use ATM today, if it is still prevalent, what different companies do, and I couldn't quite get my foot on like companies that still use it today. It was very vague in saying that it does have its niche. But for the most part, from what I read, is that the IP protocol pretty much got to the point to where it was just more practical to use. Like ATM, I don't know if I'm wrong saying this, but it kind of feels like the beta, or I think they're called the beta tape to the VHS, maybe the HD DVD to the Blu-ray. While it's good in its own right, it's just one was better and a little bit more practical, and over time was developed on and built on to where it just saw more use and it just worked better overall. Now the Internet Protocol, with its many associated protocols, it provides an integrative technology. It's more scalable and it's less complex than ATM. ATM throws this whole new concept in there where you have to really focus on the ATM switches and you really have to be invested in the infrastructure. So now IPv4 is 32 bits and it scales into IPv6, which is 128 bits. That's more address possibilities than we will ever need. That is just a huge amount. I can't even begin to quantify what the number is in my head, as I'm not too privy yet on a metric conversion off the top of my head. But since transport speeds have increased exponentially, there's no need for us to try and reduce the jitter anymore. That was one of the big things about ATM and why it was so awesome. But I mean, exponentially our speeds are growing more rapid and more rapid. I remember when they first finally installed the fiber optic around the rural community that I'm from in the late 2000s. I remember the terrible days of data, dial-up, and it's crazy to see how far we've come, but I can also understand then too, like while data has rapidly sped up in its rates, that obviously there would be less jitter overall, so what's really the need for ATM, right? Now, development of voice and video over IP protocols have provided integration capabilities for the IP suite. So you have VoIP, other things like that that we can use now through IP, to where it's just everything's bundled together. It works. Everything that ATM had, that ATM gave us, it just gives a little bit better. Since all media types can be transmitted at that level, I mean, why use ATM anymore, right? There are instances where you would. Say a small company, poured a lot of infrastructure into the ATM switches, or somewhere like, had a lot of ATM switches installed and everything. Would it be really worth it to raise that all up if it's still working? It's not completely broken. While there could be some things that would be a little bit faster, you've already poured so much money and put so much of an investment in it, you don't really want to throw that away. So there are instances. So again, sorry for going over the 15-minute limit. It was really hard for me to squish this down. I had to cut a lot off these slides, but hopefully this gave you a really good idea. I'm going to show the reference page real quick for perspective. I did put the references on the top at the heads because there was so much information. While I didn't take the only things that I did take verbatim, like word for word, I did put the superscript there. But that being said, I do want you to get a good idea of where I got this information. Specifically, number 7 from Sue and Rajan from 1995. That gave a really good idea on the ATM forum and ATM as a whole. And number 6, the Cisco Wiki. I found that one at the end, and that just blew open everything. It has everything right there. I feel like between that and the book source, which is number 3, I could have used those and went on for days about this. So again, I'd like to thank you for the time that you've taken today, and hopefully you learned something here. Thank you.